Most welcome to my new series on Laplace transformation. Laplace transformation is a fascinating tool of mathematics which finds lots of applications in so many areas. For example, we can solve differential equations using Laplace transformation. We can use Laplace transformation to evaluate some really tricky improper integrals. We can use Laplace transformation in circuit analysis because Laplace transformation has a property that it can shift the domain of functions, which is widely used in circuit analysis to represent a function or to shift a function from time domain to frequency domain. In this video, we shall discuss the motivation, definition, existence, and the beautiful geometry that lies in this fascinating concept. Before we formally define Laplace transformation, let us quickly recollect what do we mean by a piecewise continuous function. A function is called piecewise continuous on an interval if the interval can be divided into a finite number of subintervals on which the function is continuous on each open subinterval. Open subinterval means I am excluding the two endpoints, and has a finite limit at the endpoints of each subinterval. You can refer to the sketch that is there on your screen. So you can understand over the interval a to b, the function as it is plotted is not continuous, but we will call it piecewise continuous because if you consider the open subintervals a1, a2, a2b, then in each of these open subintervals the function is continuous, and as it is stated at none of the endpoint the function is having an infinite limit, or in all the endpoints the function is having a finite limit. In other words, a piecewise continuous function is a function that has a finite number of pieces in it and does not blow up to infinity anywhere. Now, let us consider the three functions whose graphs are given here. These three. Can you tell me what is coming to your mind when you look at these three graphs? What is coming to your mind about these functions? Absolutely correct. The first thing that comes to our mind is that these functions are clearly bounded, because if you look at the first one from the left side, that means ft, I can write that -1 less than or equal to ft less than or equal to 1. That means all the functional values lies between -1 to +1. That means it can be written as mod of ft is less than or equal to 1. Similarly, here I can write -2 less than or equal to gt less than or equal to +2, or we can write mod of gt is less than or equal to 2. Here also I can write for some a, I can write that 0 less than or equal to ht less than or equal to a, whatever is a. That means when this is true, actually this implies -a less than or equal to ht less than or equal to a, which implies mod of ht less or equal to a. That means this is all, and all these are true for all t, means for any value of t. You can understand that the first one, ft, is an oscillation, gt is a damped oscillation, and ht is just a damping function we are having. So that means if we now try to define a bounded function technically, what is a bounded function? That means for all the values, for all the values of the variable, of the domain variable, the function, the absolute value of the functional value should be less than a positive constant. That means if we formally define, we can say that a function ft is bounded if there exists a positive constant m such that mod of ft less than or equal to m for all t in the domain of f. So we define a bounded function in this way. Now bounded functions are very nice, very decent, very well behaved, because you can trap their values, or you can keep all their values in between two lines, as you can see in the diagrams which are above. All the entire function can be trapped or can be put in between two lines, as you can see the lines that we have in each of the diagrams. We have trapped all the functional values in between the two lines. Now if we consider these functions y equal to t, y equal to t square, y equal to t cube, what you can say about these? Are they bounded? Of course not. They are unbounded functions. We can tell them unbounded functions. Unbounded functions. Because you cannot bind them, you cannot trap them in between two lines or in that way. Means as t increases, these functional values in these functions also increases. Means these functions grows like anything. You cannot restrict their growth. Their growth is not restricted. They are growing like anything. As t increases, they will also increase. So these functions are clearly unbounded function, and clearly you can understand that if we talk about integrating these functions, we will have problems, as I discussed in my my video on improper integral, that whenever we have a function having infinite discontinuity in my domain of integration, then the integration becomes improper, and we need to be very, very careful while evaluating them. So these functions or the functions which look like these functions, they are really not too good function. They are actually, I will say, they are bad functions. They grows like anything. We cannot restrict their growth. As t tends to infinity, the functional values will also tend to infinity. They blows up to infinity as t increases. Now let me show you another function which I call a speed breaker function. I call this function y equal to e to the power minus t, where t is greater than 0. I call this function as a speed breaker function. I call this as a speed breaker function. Speed breaker. Why I call it as a speed breaker? To understand, I am claiming, or I am telling you that this function can break the speed of so many functions. This function can restrict the growth of so many functions when I multiply these functions with this function with those functions. For example, if you can see here how e to the power t, e to the power y equal to t, how y equal to t square and y equal to t cube will look like. Now see, if I multiply y equal to e to the power minus t when t greater than 0, let us see what happens. When t greater than 0, if I multiply e to the power minus t with ft equal to t, let us see what happens. The graph will look like ft equal to t. It is an increasing. Now suddenly we will say that the function will fall down and it will look like this. So if you think this is the graph of y equal to t into e to the power minus t when your t is greater than 0. So actually y equal to t was increasing like anything. When you multiply with e to the power minus t, it pulls down the function. Similarly, if I multiply e to the power t minus t with t square, let us see what happened. T square is something like this, it is going up, then suddenly it will fall down and it will keep on decreasing. It will almost tend to 0 as t tends to infinity. So you can understand this will be the graph of y equal to t square e to the power minus t. Again, if I consider the graph of t cube e to the power minus t, let us see what happened t cube e to the power minus t when t greater than 0. So y equal to t cube is growing sharply. Suddenly e to the power minus t dominates and it falls down. So y equal to e to the power minus t, I can say, pulls down t cube. So this will be the graph of y equal to t cube into e to the power minus t when t is greater than 0. You can understand all these are when t is greater than 0. So that's why I prefer to say that this function is a speed breaker. Why speed breaker? You can understand that it puts some restriction on the growth of those functions, or it pulls them down. So now these are some functions which are originally unbounded function, but when you multiply with e to the power minus t, a sharply decreasing function, then you can see that somehow you are putting a restriction on their growth, and the resultant function becomes a decreasing function. Now that means that's why I call e to the power minus t as a speed breaker, because it can restrict growth of so many functions. Now you can ask me that will it be true for every function? Unfortunately no. There are lots of functions which cannot be restricted by multiplying with e to the power minus t. For example, if you consider a function e to the power t square, now I call this function as a too bad function. This function is too bad. You can understand why it is too bad, because you can understand when I multiply this function with e to the power minus t, you can see that the resultant function y equal to e to the power t square minus t, when this t is greater than 0, you can understand still it blows up to infinity. As t increases, I can understand as t tends to infinity, e to the power t square minus t also tends to infinity. So if you multiply y equal to t square with e to the power minus t, you cannot put on a restriction on the growth. Even if you multiply e to the power minus 10t, then also you can see that the function still blows up to infinity, and it goes and it reaches to infinity, say around t equal to 10. In fact, if you multiply e to the power minus 1000t, you will say that again the function will blow up to infinity around t equal to 1000. So this is a too bad function whose growth cannot be restricted. So we have seen that there are some functions whose growth can be restricted when you multiply e to the power minus t with them. That means the resultant function will become decreasing. But there are some functions where this will not happen. Now the functions whose growth can be restricted by multiplying with e to the power minus t is known as function of exponential order. Function of exponential order. Now you can understand that if I multiply, when I am multiplying y equal to e to the power minus t, when I am multiplying y equal to e to the power minus t in each of the cases, at some point, means after some point, which you can call as a maxima, after some point the functional value starts decreasing. Now can you tell me what will happen if I multiply e to the power minus 2t? Yes, this maxima will be lower than this, means it will dominate e to the power minus 2t will dominate t or t square or t cube more compared to e to the power minus t. Or if I multiply with e to the power minus 100t, so it will pull down t or t square or t cube much faster than e to the power minus t. So if you now, that means if you consider the function y equal to e to the power minus at, that means as you increase the value of a, this e to the power minus at will pull down whenever t is greater than 0. This e to the power minus t will pull down the functions much faster than earlier if you increase the value of a. So, and even it can happen that for some function e to the power minus 5t is not being able to pull that down, but e to the power minus 100t is able to pull it down. That means for some value of a, if you see that you can put on a growth restriction to the function, then those functions are known as functions of exponential order. On the other hand, there are functions like e to the power t square. You can understand that for no value of a, you can put on a growth restriction to these values. So to whichever function you can put in a growth restriction by multiplying with e to the power minus t, or e to the power minus at, rather I'll say, by multiplying with e to the power minus at, will be known as a function of exponential order. Now if we formally define what we will say that a function is said to be of exponential order if there exists a constant a and a positive constant t0 and another positive constant m, such that e to the power minus at into ft will be less than or equal to m for all t greater than t0. That is, mod of ft will be less than or equal to m into e to the power at for all t greater than t0. So that means I have said the same thing. Once you multiply with e to the power minus at, you get the function bounded, or you get the function decreasing after a certain point. So that is whatever is written over here. Now see, if a function is unbounded, then we know that we will have lots of problem if we think about its integration. If a function is discontinuous, then also there are lots of problems if we think about its integration. If a function is having infinite discontinuity, then also there may be problems of integrating it. But think, if a function is piecewise continuous and if the function is of exponential order, can we have any advantage if we think about some kind of integration? Okay, keep thinking on this. But before that, let me show you, or let me give you some examples of functions of exponential order. So the first one, as an example I can consider, the first one, if I consider ft is equal to e to the power bt sine ct. Now I will not plot graph. I'll try to get a conclusion from this definition, because for every function it's not possible for us to plot a graph and to check the thing. So let us try to validate this definition and see what happens here. So here mod of ft will be equal to mod of e to the power bt into mod of sine ct. Now mod of e to the power bt will be equal to e to the power bt into mod of sine ct. Now you know that mod of sine ct will be always less or equal to 1. So this will be less than or equal to 1 into e to the power bt. That means I can consider this as my m and this as my a, and you can see that I am getting absolutely this kind of a relationship, that mod of ft less than or equal to m into e to the power at. So that means I can conclude that this is a function of exponential order, This is a function of exponential order. Great. Okay, fine. Now let us see another example which we have already graphically visualized. Say the second one. Let ft is equal to, say, e to the power t square. What you can say about this? So let us, actually I can use any one. I can use the first line, or I can use the second, means this form I can use, or I can use this form as well. Any one I wish I can use to validate. Both are equivalent. So here, okay, fine. Let us do one thing. Let us consider the function e to the power minus at into e to the power mod of ft. mod of ft. Mod of ft will be here e to the power t square. Let me write into mod of ft. That means actually I am talking about e to the power minus at into e to the power t square. That means I am talking about e to the power t square minus at. Now can you tell me, as t grows, means as t approaches to infinity, to which value this terminology this term approach, or this function approach? Suddenly, as t grows or as t tends to infinity, this will also approach to infinity. As t approaches to infinity, no matter what is a, no matter what is the value of a, no matter what is the value of a, right or not? No matter what is the value of a, as t grows, this will also grow to infinity. So that means what? That means you cannot put on a growth restriction, or you cannot say that as per the definition I need to have some m, so that I can say that e to the power minus at into mod ft less or equal to that m. I don't have any such m, so I will say that this is not of exponential order. This is not of exponential order. So this is how we can test whether a function is of exponential order or not. Now the question that I was telling, the issue that I was telling, that if a function is of exponential order, that means it is a decent kind of function. Means not very good, but yeah, it's manageable. That means if ft is of exponential order, then e to the power minus at into ft, that's a nice tangible function which is a kind of a kind of whose growth is restricted. And along with that, if the function is piecewise continuous, then what will happen? Will we have any advantage if we think about integrating that in the interval 0 to infinity? It is piecewise continuous and it is of the function is of exponential order. So if we think about integrating, say, this kind of an expression e to the power minus at into ft in 0 to infinity, what will happen? Okay, what I am trying to say is, let me write the whole thing down. That is, let ft, where t is greater than 0, be a real valued function that has the following properties. Number 1, f is piecewise continuous in every finite closed interval, 0 less or equal to t less or equal to b, when b is greater than 0. And number 2, f is of exponential order, then there exists a, that means if f is of exponential order, then there exists a which is a constant and two positive constants m and t0, such that mod of ft less than or equal to m into e to the power at for t greater than t0. That is the definition of exponential order as discussed above, for t greater than t0. Then what will happen? Then the claim is that then integration 0 to infinity e to the power minus ft into dt will exist. So go through the statement carefully. I'm claiming if the function is piecewise continuous in every finite closed interval 0 to b, that means you pick up any finite closed interval in 0 to infinity, that is there the function will be piecewise continuous. That means you can integrate, and the piecewise continuity tell you that in none of the point the function blows up to infinity. That means the function is not having infinite discontinuity also at any point. So that means you can comfortably integrate if your function is like that. And number 2, f is of exponential order. Exponential order means I can say that there will be some a for which e to the power minus at into ft will become a bounded function. So if these two happen, then we say that the integration 0 to infinity e to the power minus st into ft dt exists for s greater than a. For all such s which will be greater than a, this kind of an integral will exist. So if you have understood the concept of exponential order and piecewise continuity, you can visualize this result at least intuitively, that yes, this integrand is nice, it's a decreasing kind of an integrand or a bounded kind of an integrand. There is no infinite discontinuity. There is piecewise continuity for f. So yes, this integration is possible, and once I do the integration, since the integrand is decreasing kind of a thing where the growth is restricted, I can get a finite, I can get an area, because if you think this integration as an area, then you can think intuitively, yes, this area can converge, can be convergent, this area can tend to a finite number. So intuitively, if you have understood the concept of exponential order and piecewise continuity, then intuitively you can hold that yes, this result is not absurd. Okay, fine. Let us prove it analytically. So let us prove it analytically. Let us split the integral 0 to infinity e to the power minus ht into ft dt into two parts using this point t0. That means I am saying that let us split it as 0 to t0 e to the power minus st into ft dt plus integral t0 to infinity e to the power minus st into ft dt. Now see what happens if I consider the first integral in the right hand side. Then by hypothesis 1, that the function f is piecewise continuous in every finite closed interval 0 less or equal to t less or equal to b, I can consider that this function ft is piecewise continuous in this finite interval 0 to t0, and e to the power minus st is also continuous there. So I can consider, if I consider hypothesis 1, then I can say that the first integral in the right hand side exists. So the existence of this integral in the left hand side depends on the existence of the second integral in the right hand side. Now by hypothesis 2, we can say that by hypothesis 2 we can say that mod of e to the power minus st into ft will be equal to mod of e to the power minus st into mod of ft, which can be written as less than or equal to m into e to the power minus st into e to the power at, because if I use this property, this definition of exponential order, then I can have this, and which will be equal to m into e to the power minus s minus a into t. Now if we consider the integration, say integral t0 to infinity, m into e to the power minus s minus a into t dt, what we can say about its convergence or existence? Certainly we can say that this integral will converge if this term s minus a becomes positive. That means if s is greater than a, so I can say this is convergent, or this integral exists. This is convergent if s is greater than a. Now whenever this integral is convergent, if we compare this integral and the condition that mod of e to the power minus st is less than or equal to this, actually, although there is an equality, but in this chain of comparison, since there is a lesser equal to here, that sign will prevail. Actually, that means this expression is lesser equal to this. So if I use this condition that this expression is less than or equal to this expression and integration of this is convergent, so by comparison test, what we can say? Hence, by comparison, we can say, hence, by comparison test, we can say that integration t0 to infinity e to the power minus st ft dt also exists for s greater than a, right or not? If we compare, we can say that this also exists for s greater than a. That means what? That means this part of the integration in the right hand side, the first part always exists. Means when your hypothesis 1 is true, the first part exists, and the hypothesis 2 tells that the second part also exists for s greater than a. That means if I combine the two, I can say, hence, when hypothesis 1 and 2 are correct, the integral 0 to infinity e to the power minus st into ft dt exists for s greater than a. So we have proved this result analytically. Now, if you think about this integral which we are having here, just let me write the integral once more. If I write only this integral, if you think about this integral, so if I write this integral, that means I am saying about the integral 0 to infinity e to the power minus st into ft dt. If I think about this integral, can you tell me, once you we have seen that if the function ft is of exponential order and piecewise continuous as defined, then this integral will exist. That means this will have this will yield some value. Can you tell us what kind of a result you will get after you finish doing this integration? Absolutely correct. Your result will be a function of s. Pretty simple. Your result will be a function of s because you have two things here, t and a parameter s. So for this t, you are plugging in the value 0 to infinity, you are doing the integration over t. So at the end you will get a function of s. I am denoting that by capital F of s, because the function is denoted by the lowercase letter. I am denoting the result as the corresponding uppercase letter. So I am denoting it by capital Fs, some function of s. So I can think this integral as, I am as input, I am plugging in a value ft, and as an output I am getting a function of s. So I can consider this as my input and I am consider this as my output. So I can think that this particular function is like a machine where I am having some input and I am getting some output. So you can understand that in this input is a function of the variable t. That means this input is in t domain and the output is a function of s. That means the output is in s domain. That means I can consider this integral as it is transforming a function from t domain to a function in s domain. Now considering this feature, this integral is known as the famous Laplace transformation by the name of the proposer. This improper integral, you can understand it's an improper integral, is known as the famous Laplace transformation because it is Just if we think about from the geometric perspective, it is transforming the domain of the function. It is transforming a function from t domain to s domain. So it is not only an integration, actually it is a transformation. So this integration is known as a Laplace transformation. And when can we do this integration, or when the Laplace transformation exists? The Laplace transformation exists for a particular function ft. The Laplace transformation exists when this hypothesis 1 and 2 holds. That's why this particular theorem is known as the existence theorem of Laplace transformation. This is known as the existence theorem of Laplace transformation. And if we want to find out the Laplace transformation of any function, we need to check whether these two hypotheses are holding there or not. For example, let us consider a simple function. Let us consider ft, the simplest function, the constant function ft is equal to 1. So we know that ft is equal to 1 is the constant function 1. It is bounded, so certainly it will be a function of exponential order. Now let me tell you one thing which I missed probably. Every bounded function is actually a function of exponential order. What was the definition of bounded function? If we go back, yes. Now we have defined a function to be bounded if this condition happens, mod of ft less or equal to m. Now if we do a bit manipulation, we can write it further as mod of ft less or equal to m into e to the power 0 into t. Now you can understand that this fits the definition of exponential order function if you treat this 0 as a. So m into e to the power at. So yeah, every bounded function is a function of exponential order. Yeah, that has to be true. That has to be true, because exponential order function means the main logic is whether you can put on a growth restriction to the function or not by multiplying with e to the power minus at. And you can understand that if it is a bounded function, already its growth is restricted. Or in other words, if you go with this form of the definition, we say that a function is exponential order if its growth is less than the growth of some positive multiple of the exponential function e to the power at. If we compare the growth of the two functions, means a function and some multiple of e to the power at, if the growth of the function is less or equal to that, then we call it as an exponential order. That means we comparing the growth of a function to some multiple of the exponential function e to the power at. And if we find that the growth of the function of our context is lesser, then we call it as exponential order. So certainly if the function is bounded, certainly that will happen, because e to the power at grows like anything. It is one of the fastest growing function, probably one of the fastest growing function if we consider e to the power at. Exponential function will be certainly the fastest growing function. So so that means every bounded function will be of exponential order. So it's quite obvious. So here also, if we consider ft equal to 1, certainly we can say clearly ft equal to 1 is of exponential order, as if you wish, you can write the logic also as ft equal to 1 can be written as less or equal to, or actually ideally it should be equal to, but to match with the form I am writing this 1 into e to the power 0 into t. This and ft equal to 1 is continuous, because actually it is continuous everywhere, is continuous, that is piecewise continuous, means piecewise continuous, that is piecewise continuous. So what we can say, that is piecewise continuous. Hence what we can say, we can say that the Laplace transformation, hence Laplace transformation of ft, hence Laplace transformation of ft exists. Therefore, we can find that Laplace transformation of ft, actually that is ideally denoted as this kernel of ft. You can write in that way also, or since your function is 1, I can straightway write kernel of 1, or since if I use the parameter name to be s, I can write it as fs also. That will be equal to integral 0 to infinity e to the power minus st into ft as per our definition, that means into 1 dt. So that will be equal to if this is an improper integral. So how to evaluate an improper integral? If you have any doubt, you can check my previous video on improper integrals. The link is in the description box and you can see above as well. So I can write this as limit m tending to infinity, integral 0 to m e to the power minus st dt. So this will be equal to, if I calculate this, let me have some space, this will be equal to limit m tending to infinity. Yeah, this can be written as if I write it, it will be e to the power minus st divided by minus s 0 to m. So this will be limit m approaches to infinity. Let me again have some space here. Limit m approaches to infinity. Yes, this will be e to the power minus m into s divided by minus s, and t when t is equal to m, and when t equal to 0, this will be plus 1 upon s. Now you can understand that whether this limit will exist finitely or not, that will depend on what is your value, means what kind of a value this s is having. If this s is 0 or less than 0, this limit will certainly not exist finitely, because if this s is negative, you will have some positive power of this e. So that will again approach to infinity as m tends to infinity. So if this s is less or equal to 0, certainly this limit will not exist finitely, and this limit will exist finitely only if s is greater than 0, and the value of this limit in that case will be 1 upon s. So when s is greater than 0, sorry, I have given a comma here. So when s is greater than 0. So what I can say therefore I can say that based on the derivation that we have done so far, we can say that if ft equal to 1, then L of ft or fs will be equal to 1 upon s when this s is greater than 0. So if we think it geometrically, we have this kind of a situation where I have an input ft equal to 1 in t domain, and as an output, after being processed in this machine of Laplace transformation, I am having an output in s domain, which is completely a different function, a transformed function, or you can say that completely another type of function in another domain. That's why it is called a transformation. Now this change in representation or this shift of domain has become very, very useful in so many applications. For example, as I said you at the beginning of my session, that this is used widely in circuit analysis, or this is widely used in solving differential equations. Now let me give you a trivia that if you apply Laplace transform to a differential equation, your differential equation will be reduced to a purely algebraic equation, which you can solve much more easily. Isn't it interesting? You apply Laplace transform to a differential equation get transformed to an algebraic equation, which you can solve much more easily, and you can again go back to the solution of the differential equation. I will discuss everything gradually, but yeah, that's it for this video. So by Laplace transform, what we mean? By Laplace transform, we mean that this kind of an integral e to the power 0 to infinity to the power minus st ft dt, and where this s certainly is a parameter, satisfies some conditions, and this function also satisfies some conditions as I discussed. Now for the discussion so far, we have considered the function to be a real valued function, the parameter s to be a real parameter, but you will see gradually when you will learn the simple thing, and we go deeper into the study of this subject, this s can be a complex valued parameter also. That means this s can be considered as an imaginary parameter sigma plus j omega also, which becomes very, very useful. So we will discuss everything, and we will gradually move to a position where we will be able to solve differential equations effectively. But for that, we need to know some more properties of Laplace transformations of some elementary functions also, and gradually we will learn how we can solve differential equations. So that's it for this video. In the next video, I shall show you how we can find out Laplace transformation of some elementary functions, and we will discuss some properties of Laplace integrals also. So that's it for this video. Take care.